Welcome to the next video on circuit protection. We're going to talk about the construction of RCDs. RCDs are constructed in a plastic case and inside that case are 4 terminals for the external cables to be joined onto them. The phase and neutral wires are passed through a toroidal or a donut shaped sensing coil inside the RCD, and the sensing coil acts like the secondary of a transformer. There's a test button on the outside of the RCD, and inside the RCD there is a resistor that bypasses some of the current past the toroidal coil. It means that some of the current is passed through the resistor instead of the neutral, and an imbalance happens, and as a result the RCD should trip when the test button is pushed. So the coil has an output which is connected to a trip control circuit. It's an electronic circuit, and that electronic circuit works the trip mechanism of the RCD. Inside the RCD are also 2 contacts that disconnect both the phase and neutral. These are operated by the trip mechanism, and once tripped they stay tripped until it is reset. Now we're going to have a look at the operation of an RCD. In normal conditions, the RCD has current flowing in both the phase and neutral wires, and magnetic fields are produced around those wires. As the phase current is equal to the neutral current, the magnetic fields will be equal. But not only that, the 2 magnetic fields are caused by current in opposite directions, so the magnetic fields are opposed to each other, and as a result they cancel each other out. So as a result there's no overall magnetic field. You can't detect any magnetism, and no current is induced into the sensing coil. Ooh. Now we're going to have a look at a fault situation with an RCD, and first of all some current leaks out. It bypasses the neutral by going back to the supply neutral through an earth path. As the phase current is greater than the neutral current, the magnetic fields are not equal and some magnetism is left over. So we can measure that magnetism, and also that magnetism acts on the coil and induces EMF into it. The induced EMF powers the trip circuit, and that trips the mechanism. The RCD's contacts will open and current will stop flowing. So here we have a circuit showing the RCD operation during the fault situation, and you can see that the phase current is the same. If at the moment you can imagine those contacts are still closed, and the phase current is flowing through the coil to the load, through the contacts to the load. Some leaks out. You can see the green arrows, earth current leaking out around the coil, and the neutral current is smaller, the arrows are smaller. As a result, the phase and neutral are different sizes and they don't cancel out. That leaves some of the phase magnetism to act on the coil, and that turns itself into an operating transformer, and you can see the orange current arrow there going to the trip mechanism, and the mechanism trips. So once an RCD has been tripped, you need to manually re-energize the circuit. Now you'll only be able to do that once you've got rid of the earth leakage, otherwise the trip mechanism will just keep tripping out again. Now we need to look at RCD sensitivity, and that's the difference in current between phase and neutral, how small the imbalance can be detected by any particular RCD to cause it to trip. And there are different current ratings of different RCDs. Here you can see table 3 and the 2 different types that we generally use in New Zealand. Type 1 is a 10 milliamp residual current RCD, and we use those in hospitals and kindergartens and schools, and the maximum time they're allowed to take to trip is 40 milliseconds. And then there's type 2, which we generally use in domestic installations. They need 30 milliamps difference in current between phase and neutral to trip, and they need to be able to trip within 300 milliseconds. 300 milliseconds is still very, very fast, and it's still faster than a heartbeat. So that brings us to the end of this video on circuit protection.